So last week we were working on vector component addition. We were getting to the point where we could pretty reliably add two angled vectors together. We were looking at examples where, we illustrated how important scale is in the drawing and all of that. What we're going to do is actually take a little bit of a step backwards to some that are easier in terms of like the drawing part, but have another step in them, right? And we call these boat questions. Okay, so you probably want to add this example here to your notes. There's actually two types of boat questions. Okay? There are boat questions where you are rowing across a river. And there are boat questions where you are going across a river. Does that sound like it's talking about the same thing? Rowing across and going across. It's actually not. Okay? If I'm going across a river, what I'm saying is I'm actually moving straight across the river. Okay? So in a going across question, my resultant is straight across the river. But if you've ever tried to cross a river, you know that there's this pesky thing that gets in the way of actually going straight across a river called the current. Yeah, okay. If I'm going to end up doing that, I probably have to direct my rowing slightly where? Slightly upstream. I got to row a little bit in to the current to make this happen. So in a going across question, you're actually going to row at a diagonal, and the current will push you back to straight across. Okay. Is this still vector addition? I just drew those tail to head, right? And my resultant ended up being straight across the river. Okay, that happens. If I want to end up going straight across the river, like there's a dock over here that I've got to get to, I don't row at the dock. If I row at the dock, I'm going to miss the dock for sure. Okay, I've got to aim slightly upstream and let the current bring me back across. Okay, so this is what we call a going across question. Okay, so when a going across boat question, you will have your rowing velocity, magnitude and direction. You will have the current. You'll also have its magnitude and direction. It's just always downstream. And then your resultant ends up pointing straight across the river. Okay. The second type of boat question is a rowing across question. Okay. If I row across, my rowing velocity is this line. Okay. The other vector quantity involved in these is, again, the current. The current, as it would always do, would push me downstream. And my resultant would go this way. in either one of these types of boat questions, you're likely going to be asked for, actually you're likely going to be given the width of the river. Okay, so that would be this. The reason you're often given that is because one of the things you'll be asked to calculate in a boat question is how long it takes you to get across. Okay. So how long would mean I'm trying to calculate what?
Total time?
Total time. Okay. So am I likely using V equals D over T in a boat question? Yeah, because I've got a lot of velocities here, right? This is what's different. All the vector addition we've done up until now, it's all been displacement vectors. But I've told you repeatedly, it doesn't matter what vector quantity you're doing, you always treat them the same way. You draw them tail to head and you get your result. This is just kind of our first example of what that looks like when they're velocity vectors. I'm still drawing them tail to head. That part hasn't changed. Okay, so what will often be asked is how long it takes to get across. So if I'm given a going across question, what velocity do I need to use, red, black, or blue, to figure out how long it takes to get across? This is not something we've done before. I'm just use your common sense here, okay? This is measured this way, straight across the river, okay? If I want to calculate how long it takes to get across, should I be using a velocity that points the same direction as that vector? That's the thing that people often mix up or mess up in a question like this, okay? Is they'll use the wrong velocity. If I use this velocity, the red one, with this displacement vector, I'm comparing apples to oranges. This is measured straight across. This is some angle from straight across. They don't speak the same language. If I'm going to use two vector quantities together, they have to have the same vector. If you recall, back on the first day when we were talking about the trip to Walmart, okay, the displacement and the velocity ended up always having the same vector. Well, if I'm given multiple velocities and one displacement, the only velocity I can use with that displacement is the one that has the same vector. Okay, so you have to have matching vectors. So in a going across question, I would have to calculate my resultant because the resultant is the one that points straight across and has the same vector as this. In a rowing across question, I would use the rowing velocity, which I'd probably be given because that one points straight across. Okay, as does this. If I had my resultant, that wouldn't work because it doesn't point the same direction this one does. Okay, this isn't something we've covered before. I'm just illustrating to you that if you want to use two vector quantities that are measuring different things, velocity and displacement, together in a calculation, their vectors have to match. Okay, I can't calculate how long it takes me to travel 200 kilometers north using a velocity that's 20 meters per second east. Okay, if I go 20 meters per second east, I'm not going north. Okay, I'm not going to get an answer there. You kind of follow me on that? The vectors have to point the same way if I want to use them together. All right, questions so far? We're going to go through a couple of examples. Don't panic. We're going to do a few here. All right, so this one's on your worksheet. Okay, it's question 8 on the worksheet. So let's just do the first part here. Okay, let's draw it out. A boat whose speed in still water is 2.5 meters per second, okay, so that's telling me here's how fast the boat can go, is in a river whose velocity is 1 meter per second south. What is the velocity of the boat relative to the shore when the boat is headed south? Okay, so let's draw our river here. I'm just going to say that that direction is south. Okay, this is like a super easy boat question, just to illustrate the importance of diagramming it. Okay, so the river's current is 1 meter per second south. And the boat can go 2.5 meters per second south. Okay, what's the resultant speed of the boat? Or resultant velocity of the boat, sorry. Think of it this way. What's easier, rowing upstream or downstream? As a person who's rowed many boats as a fishing guide, you want to row downstream. It's really easy to row downstream because you're not fighting the current. Hey, somebody hooks into a big truck and you gotta get the boat under control. You're rowing directly against the current. It's hard work, okay? Especially if you're old like me. Okay? So you gotta work really hard. So in this case here, I'm rowing the boat at 2.5 meters per second and the current's pushing me in the same direction. My resultant velocity would be 3.5 meters per second downstream, in this case, south. Okay? Now, if instead the boat's headed north, okay, well then I would have my current and my rowing speed. Oh, sorry, it's north. Sorry, I drew that wrong. Okay, so they're still drawn tail to head. Okay, this is fish on. I gotta roll upstream now. Gotta row directly against the current. Right, now my resultant velocity is going to be 1.5 meters per second north, or upstream in this case. Okay, and then for C, if the boat's headed west. So let's get rid of that. Okay, so boat is headed west. So if that way is south, west would be this way. Okay, if I put those two vectors together, that's what the boat's going to do. Agreed? Okay. All I'm doing is drawing these things tail to head, just like I would any other vector quantity. It doesn't matter that these are in meters per second and the ones we were doing last week were in meters. They're all treated the same if they're vector quantities. Now, here's what's different. Okay? In a displacement question, one thing happens, then the other thing happens, then the next thing happens. When you draw it, you actually know this one happened first, this one happened second, this one happened third. These two are happening at the same time. That's okay. Right? Two things can happen at the same time. Right? If I had, it would just imagine if I had like a drone flying over top of this. Right? I wouldn't see this and this, I would see this. They're happening at the same time, but the end result is the same as if one happened and then the other. Okay? I still draw them that way, but I understand that they are going on at the same time. Okay, so this would be my resultant right here. Okay, I would just do Pythagorean theorem, 1 squared plus 2.5 squared. That'll give me 2.7 meters per second. Okay, and then my vector would be 22 degrees south of west after I do the trigonometry. Okay. All right, everybody okay with how we draw those? And that it's actually no different than we draw anything else. Okay. Okay, I'll give you a minute to copy that down. Okay, so our diagram is going to look something like this. Okay, we know that the river has a current of 1.2 meters per second. Okay, so I can put that on there. 1.2 meters per second. Okay, and I know that the person can row at 3 meters per second. I know to draw that there because the question stated to me that the person is going directly across. Okay, so my diagram should look like that. They told me the resultant is straight across. They didn't tell me how fast. They just told me they're going straight across. Okay, and that they can row at 3 meters per second. Now, if you're rowing slightly into the current, your boat's not going 3 meters per second. That might be how fast you can row, but you're not going to end up going that fast. You're going to end up going a little slower, which this diagram clearly shows. So the first part of the question wants to know what's their heading? What direction do they need to row? Which direction do they need to point the boat? Okay, it could be asked a number of different ways. Okay, but the angle here is our heading. Okay, that's what part A wants us to find. Right? Can I find that? Right, I just have to do some trig here. I have the hypotenuse and the opposite side. Right? I should be able to find that angle. All right, so for part A, okay, theta is going to be the inverse sine of opposite, 1.2, over hypotenuse, 3. Okay, now that angle is actually not the angle they asked for. Okay, this sometimes happens in a question like this. In a boat question, they may ask for a specific direction. Okay, so I calculated this angle right here to be 23.57 degrees. But that's measured from straight across. Where do they want it measured from? They say, what direction are they rowing relative to the starting shore? Well, the starting shore is over here. So they actually want this angle. Do I have to do more trig? Nope. This is the complementary angle, right? If that one is west of north, this one is north of west. They're the complementary angles to each other. So all I have to do is go 90 minus, and I've got the angle they actually wanted. Okay, that happens a lot in these kind of questions, and people sometimes forget to check. Did they specify where they wanted the angle measured from? Right, so in this case, we would say 66 degrees from the southern shore, or from the starting shore. So in a going across question, it is very common to be asked for a heading. Okay. Now, the second part of this question, they want to know if the river's 20 meters wide, so there's an additional given that I can put on my diagram. The river's 20 meters wide, how long does it take to get across? Can I use either of the two velocities I was given? One points downstream and the other points 66 degrees from shore. Is either one of those pointing straight across? Okay, so what do I need to do first? Yeah, I could use Pythagorean theorem or I could use trig. Either way will get me that third side of the triangle. So you could go c squared minus a squared equals b squared and get that side, okay? Or you could just say that that's the adjacent side and do a trig calculation to get it as well. Okay, I'm gonna do it that way just because I think it's quicker that way. Okay, so I'm gonna use this angle right here that I calculated, okay, along with the hypotenuse to get that side. Okay, so for part B, I'm gonna go V equals the cos of 23.5 degrees, and with all the decimals obviously, times the hypotenuse. Whoop. But I should probably do what I said I was going to do. Times 3. All right, so that side there is 2.75 meters per second. Can I use that along with the distance across the river to find out how long it'll take? Now it's just a V equals D over T question, right? I've got V, I've got D, all I have to do is find T. So T would equal D over V. 20 meters wide divided by 2.75 will give us our time. Right, so it's going to take us 7.3 seconds to get across. Okay, is there any one part of that that's super hard? The combination of steps can be a little tricky, okay? But I mean, you had to do V equals D over T, you had to do a little bit of trig, and you had to subtract 23 degrees from 90. Okay, there's nothing super mathematically challenging about these. It's the context that gets people. Okay, and you're going to get a lot of questions like that in Physics 20, where there's a story that you have to read. Okay, and you got to get all your numbers out of the story. And the reason we're doing that, it's actually a big focus for Mr. Dickey and myself this year, is because the diploma exam has really gone that way. Okay, we're seeing more and more this big long blurb about something, and then using all of this information to answer the next two questions. Like we actually had one a few years back on the diploma exam where it was literally a page and a half of reading to answer one question. That was an extreme case. We never saw that again. Okay, but there's lots of times where it's, here's a half a page of text about what seems like an unrelated story. Okay, and now do these two calculations with that information, and you've got to pull from that paragraph or half a page or whatever. Okay, it's talking about this concept they went over. I know I need numbers like this. Oh, there's one, there's one. I can pull them out of there and go for it. Okay, so we're trying to kind of get your feet wet on that in Physics 20 a little bit by making you do questions that have a story behind them. Okay. All right, that's a going across example. Okay, let's do a rowing across example. give you a minute to get that copied down. All right, so let's draw the diagram for this first. Okay, here's our river. Right, and we know that the current on this river is 1.1 meters per second downstream. And we know that the person can row at 2.8 meters per second. And they're rowing straight across. That means that if I had a drone watching this from above, what I would see is a boat moving diagonally across and down the river. Okay, is that the angle they want? No, they want this one, which is fine. We'll just go 90 minus to get that. Okay. All right, so I need to find the resultant velocity of the boat. Is that a pretty easy calculation? I have to do Pythagorean theorem and trig, and then I'm good on that. Okay, so to answer part A, first thing we would do, right, would be to go that V equals 1.1 squared plus 2.8 squared. That'll get us the magnitude of that velocity. Okay, so what? Exactly 3. Okay. All right, so there's the magnitude, 3.0 meters per second. I also need to vector because it's resultant velocity, which has magnitude and direction. All right, so I'm just going to use tan because I have the opposite and adjacent sides. Okay, so tan to the minus 1 of 1.1 over 2.8. Okay, or could I save myself time and just flip those to get the other angle? Right? Could I just imagine that I'm looking for this angle in a triangle that's 2.8 on this side by 1.1 on that side? It's okay to do that too, whichever way makes more sense to you. Okay. 2.8 divided by 1.1, that'll give me the right angle directly. Okay, 69 degrees from the starting shore. Okay, so 3 meters per second at 69 degrees from the starting shore. Okay, right, that part's fairly straightforward. They're just perpendicular vectors. All right, questions on the first part? Okay, now, how far downstream will they be when they reach the other side? That might be a little trickier. I know how fast they're going that direction. What do I not know? The time. I don't know how long it takes to get across, but could I find that? Well, I know how far across the river is, right? It says it's 35 meters wide. Okay, and I know I'm going across it at 2.8 meters per second. Those two things are going on concurrently. Okay, so I should just be able to go T equals D over V, okay, and go 2.8, or sorry, not 30, sorry, 35 over 2.8. On the top. 35 meters over 2.8 meters per second. All right, so it takes 12.5 seconds to get across. Now, sometimes people look at that and go, so that's how long it takes to get across. That has nothing to do with how far downstream I'm going to go. Are they right? Or are these two velocities happening not only at the same time, but for the same amount of time? Right? I would be going downstream at 1.1 for as long as I'm going across at 2.8, because once I get to the other side, both of those stop. Right? I hit the other shore and I'm done. I drop the anchor and I'm not going anywhere. Okay? Does that sort of make sense? So if I find the time to get across, that's also how long I'm going downstream. So I can use that time for 2 of those dimensions, or it applies to 2 of those dimensions. Okay, so now I could figure out how far downstream they will be. D equals V times T. I just calculated T, and I know the current is taking me downstream at 1.1 meters per second for 12.8 seconds. 12.8 or 12.5? 12.5. 12.5. Okay, so 1.1 times 12.5 seconds, and that's how far downstream I'll be. Okay, 13, actually we only have 2 significant digits, so we're going to say 14 meters downstream. Okay, so again, no serious math in that question. V equals d over t, a trig calculation and a Pythagorean theorem calculation. But you do have to understand that in a trip like this, you have 2 things going on at the same time for the same amount of time. Okay? All right, everybody okay with those? Okay, so now you've got an example of each type of boat question. There's always a boat question on the unit exam. Oops. Oops. Okay, try that one. Okay, if you want to travel north perpendicular to the river current, are you going across or rowing across? So this is a going across question. Okay, if you want to go perpendicular to the current, that is straight across. Okay, so this is a going across question. All right, guys, so let's just have a quick look at this one here. So it's a going across question, okay? So we know that the resultant is straight across the river. Okay, we know that the river current is 1.2 meters per second east. Okay, and the person can row at 3 meters per second. Okay, so that's our triangle. The question just wants, what's the heading? What direction must the boat head? Which means you could calculate this angle or this one. It doesn't specify. Either one would be right. Okay, this is not a question where it said measured from the southern shore or starting shore. Then you would have to give a specific angle. Because it only asks for the heading, you can give either one of those angles as long as you have west of north or north of west appropriate on each one. All right, so all we're doing is looking for the heading. Tan to the minus 1. Sorry, can't use tan because we have the opposite side and the hypotenuse. So sine to the minus 1 of 1.2 over 3.0. Okay, that'll give us the 24 degrees. And that'll be west of north. And if you did it the other way, or you went 90 minus, okay, then you got 66 degrees north of west. Either one is possible. Yeah. Okay, everybody all right with that? That would be a fairly simple going across question because it only asked you for one thing. There was no follow-up, like how long does it take to get across this meter or this river if it's 50 meters long. Okay. All right, anybody need that one anymore? We just did one like that. Okay, try that one. By the way, a plane is a boat that goes in the sky. So this is a boat question. Okay? It just has a plane in it, but a plane is a sky boat. shoot, I left that recording the whole time. Oh well, there'll be a big gap in the middle of that. Okay, so the pilot wants to fly west. In other words, our resultant is due west. Okay, the plane has an airspeed of 95 meters per second, and there is a wind blowing 25 meters per second north. Okay, so I'm going to draw in the wind in green going north at 25 meters per second, and then I'll know where to draw the speed of the plane. It's got to connect here so that my two vectors that I actually have are tail to head. This is the resultant. Okay, so I actually drew the resultant first, and then I connected the dots afterwards. All right, so this is my 95 meters per second. If I want to end up going straight west and there's a northerly wind, I probably have to aim the plane a little south of west. Would you agree? Okay, I mean, always kind of talk it through in your head and visualize it. If I want to end up going straight west, but there's something pushing me north, I got to aim slightly into that so that I end up going the right way. Okay, so what direction must we head the plane? All right, well, that's theta. Now, that's probably not the greatest scale diagram, but there's not much else to do with it, so it's not terribly important there. All right, so I'm looking for this angle. I've got the hypotenuse on the opposite side, sine to the minus 1 of 25 over 95. That's a 995. Okay, and that's going to give me 15 degrees south of west, which is a reasonable angle for me to point the plane if I want the wind to push it back to due west. Okay, everybody all right with that? Okay, so you've done a few going across questions now. Yeah, try this one. All right, so here's our river. Okay, and they are heading directly north across a river, moving at 4 meters per second. Okay, so here's our 4.0 meters per second. Okay, the current is 2.1 meters per second east. And the width of the river is 125 meters. Okay. So part A, what's the velocity of the boat with respect to the shore? All right, so here's my resultant, like that, but they want this angle right here, which means I can find the one that's inside this triangle and go 90 minus, or I can shorten my work and recognize that this makes a rectangle. That would be 2.1 on this side and 4 on this side, and just find that. Okay, so I'll find that angle first. So that'll be inverse tan. 4 divided by 2.1. Okay, so 62.3 degrees. Okay, so actually this angle, should correct that. That angle's not right because that's the complementary angle. Okay, my angle of 62 degrees is correct. Okay, and that is north of east. Okay, I also need V. That's just a Pythagorean theorem calculation, 2.1 squared plus 4 squared. Okay, that's going to give us 4.5 meters per second. Just so we got that number in there, 2.1 squared plus 4.5 squared. Okay, so, oh, why did I put 4.5 squared in there? That's the answer. Yeah. All right, questions on part A? Okay, now, for part B, how long does it take the boat to reach the opposite shore? Well, the opposite shore is directly ahead, 125 meters, and I'm moving in this direction at 4 meters per second. This is the velocity I use. Here's what happens to people on a test if I give them this question. They naturally become attached to this answer because they've worked so hard to get it, and it must be used again somewhere, except it isn't. Okay, you just work hard to get this answer because it's the answer to part A. It is completely irrelevant after that. It does not point across. It does not point down. It points 62 degrees north of east. None of the other questions are related to that direction. Everyone kind of follow me there? All right, so I use the 4 because it's due north. I use the 125 because it's due north, and that will help me to calculate how long it takes to get across. So 125 divided by 4. All right, so I'm going to be rowing for 31.25 seconds. Now, in this, I would only have 2 significant digits, so I would say 31 seconds. Now, I know I haven't gone over significant digits in detail yet, and I will, okay? But here's just a little tip for you. If I use this number, which I calculated as the answer to B, for part C, this is the part I use. You use your rounded value, okay? So if you calculated something as a final answer in part A or B, and you're using that final answer to calculate something in part C, it has to be already done. You have to use the number of significant digits you figured out for the previous part. Don't use the full value. You hold the full value in your calculator until you arrive at a final answer, okay? If you have to use that final answer to do a second part, you use the rounded value. Okay. All right, for part C, how far downstream is the boat when it reaches the opposite shore? Okay, well, as I said, I'm rowing for 31 seconds. That means I'm traveling for 31 seconds, both across and down. So to get that downstream distance, okay, D will equal V times T. That'll be our 2.1 meters per second times now 31 seconds. That's going to get us 66 meters. Okay, everybody all right with that? Okay, all right, so that's a very typical rowing across type of question. Okay, now, on a test or a quiz, you might get a little more context with that. Okay? In previous semesters, we've talked about ferries that take things across really big rivers. Okay? And we talk about the context of that particular ferry. Okay? Stuff like that. Just, you know, or it could be, again, a passenger airliner is trying to fly from this city to that city, and it's got to go along this path, but there's a wind that, so there's going to be story there that you have to pull that stuff out. Okay? All right, what do we got for time here? Okay. I'm going to give you guys about a 5-minute break here, and then I'm going to throw one of the ones from last week, or a question like that up where you got to do the diagram. Okay, but just so you saw some boat questions, so you know what to do with them. Okay. Okay. Oh, I must have been lazy. I probably kept the unrounded value. Yeah, guys, that should, I think that comes out to 65, right? Yeah, I probably was just quickly trying to make up the key and kept the rounded value, so what a hypocrite I am. Yeah, that should be 65. Relative to something, because the angle arc is touching that thing, and that's the angle. Yeah. Yeah. Also, we're still recording. Oh, we're still recording. Thank you. Okay, guys, let's give that one a try. Okay, so this is like what we were doing last week. Tail to head, vector components, find your x's and y's, all of that kind of stuff. Okay, even though it says it's a boat, it's sailing, not going across a river. Okay, unless a river is mentioned, it's a vector question, not a boat question. Boats are in the river boats. All right, so our first vector is 20 degrees east of north, okay, and it's only 150 kilometers, so. Oh, east of north. I gotta draw it the right way though. That's helpful. East of north. So here's due north, 20 degrees east to north. 150 kilometers, X and Y, and then 265, that's 45 degrees south of east. So, okay, there's east, 45 degrees south of east. That might be a little long. Just erase a little bit of that. Okay, so again, scale's important on that one. My 45-degree angles, yeah, it's probably a little shallow. It could probably be a little steeper, okay? But it's generally going to get the point across. Okay, so my resultant should go like that. If you drew the triangle this way, that's also fine. It doesn't matter which way you go. Okay, guys. Let's go through the solution to this one here. So next step, once we have the diagram drawn, is to find all our x's and y's. Green x is the opposite side to the 20-degree angle. So we'll have sine of 20 times 150. All right, so that side's going to be 51.3. And that's kilometers, and that is east. Okay, and then for y, it's going to be the cos of 20 times 150. Okay, so that side's 140.95 kilometers north. Okay, then for x, for red x, okay, it's the adjacent side to the 45-degree angle, so we'll go cos of 45 times 265, and that'll be 187.38. Sorry, we said that was 187.38 kilometers, and that is east. And because it's a 45-degree angle, this is also 187.38 kilometers, but it's okay. Then, now that I've got all the x's and y's, I can calculate how far over x, my resultant, goes, and how far down, in this case, it goes. So the two x's are both east, so we just add them together. So we'll have our 51.3 plus our 187.38. Okay, so that's going to be 238.67 meters east. And then for our y, green y is north, red y is south, so we'll have to subtract the two of them. So we'll take our 187 there, okay, and we'll subtract the 140. And our resultant y is going to be 46.43 kilometers south. Okay, and now we can get our resultant's magnitude and direction. So first Pythagorean theorem with the 238 squared plus the 46 squared. Okay. Okay, so 243 meters. Sorry, kilometers. And then to get theta, y is opposite, x is adjacent, so theta will be 10 to the minus 1 of 46 over 238. Okay, so we're looking at 11 degrees, and for me, that direction is south of east. 11 degrees. But we only have 2 significant digits, so this should actually be 2.4 times 10 to the 2 kilometers at 11 degrees south of east. Okay? For this week, guys, you do have a quiz this Friday. It is just going to be on vector addition, so the stuff that we've been working on. Okay? The appropriate practice quizzes would be 7, 8, and 9. Okay? And the solutions are obviously in the
Can you
video
please
format.
stand for the praying of the Angelus?